More on polynomials. So let's talk about complex zeros. So these two theorems tell me that if I know that I have a complex zero of the form a plus bi, where a and b are real numbers, I is the imaginary unit I, a plus bi, then if this is a zero of the polynomial, so is its complex conjugate, a minus bi. All right, so I want to find a cubic polynomial in standard form with real coefficients having zeros at -3 and 6 plus 2i. So the theorem we just looked at told me if 6 plus 2i is a zero, then so is 6 minus 2i. So now I've found all three of my zeros. I can form my cubic polynomial. It'll have some number a times x minus the first zero, -3, times x minus the second zero, 6 plus 2i, times x minus the third zero, 6 minus 2i. All right, so now the first thing I notice is the coefficient is a 1, so that tells me a is 1. So I'll just drop the a, and x minus -3 is x plus 3. Now these two, I'm going to regroup them. So I'm going to distribute the negative, and I'm going to have x minus 6 minus 2i, and then x minus 6 minus and minus will make that a plus 2i for the last term. Now notice here I have an x minus 6 and here I have an x minus 6. And then here I have minus and plus, the same thing. If I regroup the minus 6 together in these two terms, I can FOIL this quicker as a difference of squares. That's a shortcut here. So I'm going to have x minus 6 times x minus 6 is x minus 6 squared. X minus 6 times plus 2i and x minus 6 times -2i will subtract off. And that's why I did that regrouping, as these two terms will be gone every time. Then minus 2i times minus 2i would be a minus. 2 times 2 is 4i squared. All right, so this is x plus 3 times. Now I'm going to go ahead and FOIL this. X squared minus 6x minus 6x is minus 12x. Plus minus 6 times minus 6 is plus 36. And then the I squared is a -1, so that becomes a plus 4. And I'm looking at x plus 3 times x squared minus 12x plus 40. Now, distribute the x through and distribute the 3 at the same time. So x times x is x cubed. Minus 12x squared plus 3x squared will be minus 9x squared. Plus 40x minus 36x is a plus 4x. And then plus 3 times 40 is plus 120. So there's my polynomial in standard form. Now let's find a polynomial having zeros at -7 and 2 minus I that satisfies the requirement p of 1 equals 9. Well, again, if 2 minus I is a 0, so is its complex conjugate, 2 plus I. So my zeros are, okay, I've got some constant times, x minus -7, x minus 2 minus I, and then x minus 2 plus I. So again, I'm going to regroup here, make this x plus 7 regroup to x minus 2, minus and minus makes that a plus I, and then x minus 2 gets grouped over here, and the minus I is on the end. All right, so now foiling. X minus 2 times x minus 2 would be x minus 2 squared. Minus and plus, the same thing will go away, and then minus I squared will become a plus 1. So I have some number times x plus 7. Foiling here, x squared minus 4x plus 4, and then this becomes a minus -1, so plus 1. So I'm looking at some constant a times x plus 7 times x squared minus 4x plus 5. Distribute the x through, and I'd have x cubed minus 4x squared plus 7x squared is plus 3x squared. Plus 5x minus 28x would be minus 23x. And then 7 times 5 is 35. Okay, now p of 1 is supposed to be equal to 9. So if p of 1 equals 9, then that means that 9 should be equal to a times 1 plus 3 is 4, minus 23 is negative 19, plus 35 would be 16. So my A must be 9 over 16. So I would have 9 over 16 x cubed plus 27 over 16 x squared minus 23 times 9 over 16. So what's 23 times 9? That would be 180 and 27, so 207. And then plus 35, again, doesn't cancel with the 16, so 35 times 9 over 16. So that would be 350 minus 35 is 315. All right, so there's our polynomial that satisfies those requirements. All right, now, every function defined by a polynomial of degree 1 or more has at least one complex zero. So, if p is a polynomial of degree 1 or more, then there is some number k so that p of k equals 0. In other words, I can factor it into x minus k as a factor times some other polynomial, and that polynomial can also be factored. So, I could keep factoring on down. Basically, what we're saying here is if we consider complex zeros, every polynomial can be completely factored into linear factors like this one. Now, what we said before was that every polynomial could be factored into linear factors and irreducible quadratics. Irreducible quadratics are the ones that have complex solutions. So if we allow for complex solutions, we can always go down to this linear factor form. A function defined by a polynomial of degree n has at most n distinct complex zeros. All right, let's find all remaining zeros of this polynomial given that negative 5i is a zero. Well, notice that if negative 5i is a zero, then so is positive 5i, its complex conjugate. So I know two zeros, or two factors, would be x minus negative 5i and x minus positive 5i. So if I multiply out x plus 5i times x minus 5i, I get x times x is x squared, minus 5ix plus 5ix, those subtract off, minus 5 times 5 is 25i squared. That's x squared plus 25 when I replace the I squared with a negative 1. So I know that one factor of this is x squared plus 25. So that means if I do long division, x squared plus 25 into this polynomial, 2x to the 4th minus 2x cubed plus 55x squared minus 50x plus 125, I should get a remainder of 0. Let's do it. So what do I have to multiply x squared to make it look like 2x to the 4th? That's 2x squared. So 2x squared times x squared is 2x to the 4th. 2x squared times 25 is 50x squared. Subtract. I get negative 2x cubed. That would leave a 5x squared. Bring down the 50x. All right, what do I have to multiply this by to make it look like that? A negative 2x. Negative 2x times x squared is negative 2x cubed. Negative 2x times 25 is a minus 50x. Subtract. That's a 0. Bring down the 5x squared. That's a 0. Bring down the 125. What do I have to multiply this by to make it look like 5x squared? That's a 5. So 5 times 5x squared, 5 times 25 is plus 125. Subtract. You get a remainder of 0, which is supposed to happen because it's a factor. But that means this is my other factor. So p of x can be factored into x squared plus 25, this guy that we found up here, times 2x squared minus 2x plus 5. So I just need to factor this to get the remaining zeros. I can also use the quadratic formula. X equals negative b is 2 plus or minus the square root of b squared would be 2 squared, so 4 minus 4 times a times c over twice a. So that would be 2 plus or minus square root of 4 minus, that's 2040 over 4. So that's 2 plus or minus, that's negative 36. So I, and then square root of 36 is a 6. So let's reduce that. That's 1/2 plus or minus 3 over 2. So find all remaining zeros. My remaining zeros are 5i and 1/2 plus or minus 3/2 I. Now the multiplicity of a zero is the exponent on it that appears when it's in factored form. So this has an exponent of 1, so 0 is a multiplicity of 1. Negative 2 is a multiplicity of 2 because of the exponent. And positive 1 is a 0 of multiplicity 3. Find a polynomial function with real coefficients of least possible degree having a 0, 2 of multiplicity 3. So that means that we would have a 0, 2 of multiplicity 3. So x minus 2 cubed. A 0 of 0 of multiplicity 2, so x minus 0 squared. And a 0i of single multiplicity. That's x minus I. But remember, if I is a 0, so is its complex conjugate. So x plus I must also be a 0. So I would have exactly what I wrote here, right? The x minus 0 is x squared times x minus 2 cubed times x minus I times x plus I. Now, if I multiply that all out, it becomes this mess. This is one of infinitely many such polynomials. Remember, I put the a there. This is just the one with a equals 1. I could have a be anything, and it would still satisfy this criteria. So I could multiply it by any constant value, and it would do the same. Now, notice at 0 with the multiplicity of 2, we kind of turn off of it. Notice at 2 with the multiplicity of 3, we pass through it. Notice down here we have a little zig in the polynomial where we can't see, but these imaginary zeros create that waviness to the function. When I've got a multiplicity of 1, we pass through the 0. When I have a multiplicity of 2, or any even multiplicity, I bounce off the 0. When I have an odd multiplicity, 3, 5, 7, it passes through at a curvature.